So the next talk is a distinguished paper and will be given by Yawen Guan from EPFL, also about trees, among others. So please start.
Yeah. So hi everyone, my name is Yawen, and I'm going to talk about the work with Clément on precise reasoning about containing internal pointers with logical pinning. So time for a puzzle. How to verify this program? But no worry, I'm going to walk you through. So the first, let's assume there is a linked list storing the lowercase character ABC at pointer P, at the location P. And then we call the M function with index 1, which is going to expose an internal pointer pointing to the first element B. And then the to upper is essentially a map operation that is going to update the lowercase character into the uppercase ABC. This operation preserves the internal pointers so that R remain valid to be used to update the element B to X. This simply is very simple 3-line example. It's actually surprisingly difficult to verify. If you write in a language like Rust, the borrow checker will reject it. If we do interactive theorem proving, most of the state-of-the-art separation logic approaches will find very complicated or even impossible to verify. This includes the magic one operator, of course, and many more others. So in this talk, I'm going to tell you, I'm going to first briefly introduce separation logic in one slide, and then I'm going to tell you why containing internal pointers are difficult to reason about. And then I will give you the key idea, the key insight, which is also the takeaway of our talk. And then I'm going to give you a step-by-step explanation of our proposed solution called logical pinning. Our target is the sequential programs that is written in the pointer manipulating language like in C. So, separation logic. The core idea of the separation logic is separation. Separation is to divide resource into disjoint part. The basic construct is called a separating conjunction. For example, P points to V, star Q points to U. The left-hand side talks about a cell allocation P storing value V, and the right-hand side talks about a cell allocation Q storing value U. And the star ensures that these two cells are disjoint, so P and Q cannot be alias. A container, like a linked list, is represented as by the representation predicate in separation logic. The typical representation predicate of a list says that if the list is empty, then P is the non-pointer. Otherwise, P points to the head element of the list. And then at P+1, at location P+1, we find the intermediate pointer Q, which recursively points to the tail of the list. We can notice that this intermediate pointer, these internal pointers, they are hidden in the representation predicate behind the essential quantifier here. And then, therefore, it's not showing up in the top-level logical model. This is good for modularity, but it makes this internal pointer difficult to reason about. The first observation we have is that exposing the address of a subplot is usually over-approximated as borrowing. So look at our concrete example. Now we can replace the diagram with the representation predicate, and the state after the nth is usually modeled as R points to B, saying that R borrowed the element B from the list to become its exclusive owner, and then leaving the rest of the list that is stored at location P. And then notice that to upper actually wants the full list ABC. To get that, we have to revert the borrow to return the element B back to the list. And this process, we lose information. We forget about R, which we need to use later. The second observation is that traditional sophistications are imprecise. They do not capture pointer stability. Pointer stability is a property of container operation that talk about that the operation preserved all the possible internal pointer of the container. It's widely used in low-level programming like C and C++. And in our example, we know that to-upper actually preserved the internal pointers. And we also know that to-upper is essentially a map operation. Well, easily we know how to specify a map, right? The typical specification says that if you give me a list, that I'm going to update every element of the list to the uppercase. However, this sophistication actually allows implementation that move the element around, so that R may end up pointing to some invalid memory. actually pretty surprising to me personally to see that this beautiful, elegant, simple math sophistication that we have been using for years is actually imprecise. So, based on these two observations, we propose logical pinning, which is a lightweight borrowing model and proof discipline for precise reasoning about continuing internal pointers. We have two key ideas, and I'm going to talk about them one by one. The first key idea is that in the continuous logical model, we are going to annotate each borrowable subpart with its fine-grained borrowing state. So previously, we have this list ABC allocation P, and then we are going to refine the predicate list to list prime to allow us to annotate the element with this borrowed state owned. Everything is owned at the beginning. And for the borrowed state, now we can say that the first element is borrowed at location R. We have this bracket because we actually check a list of its both internal pointer to that specific element, so it's a singleton list. We can see that in this kind of borrowing, in this kind of modeling, we go directly from the owned state to the borrowed state, which does two things at the same time. It not only it's both the address R, but also do the ownership transfer. However, the ownership transfer is not needed. It's an over-approximation here because we actually don't really need the ownership transfer here as we have already seen before. So instead, we have the fine-grained borrowing states. So we introduce the intermediate state called offered, saying that B is offered at location R. So we still have the ownership of B, but we offer it at location R for other people to borrow in the future. So we decouple the address exposure and the ownership transfer. And it allows us to actually go back and forth purely logically between the offered state and the borrowed state. And then if we don't want the exposed location R anymore, we can forget about it by going back to the own state. So now instead of like borrowed, we use offered here to just expose the address R. And then we can do the ownership transfer later when we actually need it. So the second key idea is that we can capture pointer stability with a precise classification of rise. So we have already seen two different kinds of rights here. The first kind, we call them in-place rights that update the content exactly at their original location. The second kind, we call them full rights, which may relocate or deallocate elements. The first kind, they don't invalidate existing pointers, so they preserve pointer stability, while the second kind does not have this guarantee. So we know that two-upper is one example of the in-place right. So we can capture the pointer stability by saying that it's going to preserve all the borrowing state and all the exposed internal pointers of this input state. So we have this offer state at the end here. And then we do the ownership transfer later when we need it. So to combine these two key ideas together, now we can see the full proof coming out. So at the beginning, everything is owned. And then after nth, we expose B is offered at location R. Two-upper is going to preserve all these borrowing states. So it becomes capital B offered at location R. And then we do the ownership transfer here. We call it a logical borrow to detach the ownership of the element B out of the list. And then after the local reasoning, and then we can do the revert of logical borrow. We call it a logical return to put the element back. And then after all of this, if we don't need R anymore, we can do a logical forget to forget about the exposed location R. So logical pinning. In this work, we show that logical pinning allows precise sophistication of realistic APIs for lists, for trees. And then we show that it's practical by showing that it assumes some well-known proof patterns. It simplifies some complex proofs, and it also enables reasoning about program pattern that is not allowed, not supported by the traditional sophistication. And we show logical pinning is compatible with most separation logic variant. You only need to change the way to write sophistication and representation predicate. And we formalize it. We formalize the borrowing model and all of our result in one of the separation logic framework called CFML in ROC. So next, I'm going to give you a step-by-step explanation of logical pinning. And I'm going to show you how to use it as a proof discipline in 4 steps. And I'm also going to tell you about the state of the borrowing models. So the first step is the preparation step to prepare ourselves. So start from the typical sophistication of a linked list. We notice that we have this indirection introduced by the intermediate pointer. We are going to abstract it away by denoting it as the little star applied to the list predicate. We call it indirect predicate transformer. And then so that this predicate says that at location p+1, we find the list L indirectly stored. So it's just syntactic sugar. You can understand it as notation. So then we will write it. And then we find, and then we all notice the pointer arithmetic p and p+1. We can also do abstract it away by introducing a record, which has 2 fields, element and x. And the first field store x, and x is described by the predicate cell, which essentially points to predicate, but simply says that x is going to be stored in a cell. And then the next field L, the next field next, it's described by this indirectly stored list. So we will write it again. OK, so now we finish our preparation. Time to do the real work. So first, we need to identify what exactly is the borrowable subpart. In our example, it's this list element, the characters. And their logical model is this little chart, the character here. And their representation predicate is this cell, the points to predicate. So now we are going to refine our representation predicate from list to list prime to check the borrowing states. So for the logical model, we change it to borrowable characters, where the borrowable type is going to encode all of these borrowing state. We have 4 states in total. And then the others are the same, except for the representation predicate, we have the little b. It's like the little star, it's also a predicate transformer. So B cell is going to describe a borrowable cell instead of just a normal cell. We actually use the same notation for the logical model and the representation predicate. So we only need to write the little b char and little b cell. So you can see the only difference between list and list prime is just we apply the little b on both the logical model and the representation predicate of the borrowable subpart. And we say that we have 4 different borrowing states. They are owned, offered, borrowed, and missing. They are actually modeled by a pair of option of value and a list of alias, a list of exposed pointers to that specific object. When the option is sum, we say that when the value is available, we have an aggregated state called available. On the other hand, if the option is known, we say that the value is unavailable. If we know that the list, the exposed internal pointer list, has at least 1 exposed address, we say that this object is got pinned to that specific address, so you cannot move it in the memory without changing its borrowing state. Otherwise, we say that it's logically floating in the memory. You can freely move it, and then logically it's OK. There are a lot of transactions among these borrowing states, and we already know some of them. For example, from own to borrow, we know it's pointer exposure. And then between offered and borrow, we know that it's ownership transfer, that you can go down, you can go to borrow state by a logical borrow, and you can go back by a logical return, and you can both back and forth, back and forth. And then we know that from offered to owned, we are going to forget about the exposed pointer. We do the logical forget here. And the second step, now we know how to refine the containers like representation predicate to capture these borrowing states. Now we are going to enrich the API sophistication to reflect the validity of these exposed internal pointers. So the first is the AND function. We know that in our example, it converts the owned B to the offered B. So what does this sophistication look like? Well, we need to say that if N is like valid, it's less than the length of the list. And then if we have a list L, list L described by list prime. And you can notice here, list prime actually allow all kinds of borrowing state. So this element, the interested element, can be owned, can be offered, can even be borrowed. We don't care, because env is actually a function that only cares about the underlying shape, the underlying structure. It doesn't care where the element is here or not. And then, and then in the post condition, we are going to update the env element depending on the original state of the env element. If it's originally pinned, if it's originally floating, then we are going to pin it down to the location R. So on will become offered and missing will become borrowed. And otherwise, if it's already pinned, then we are just going to remember one more alias. So in the entire pattern matching, we can encapsulate it in the function called pin ln at location R. The second function is the two-up function, the map operation. So let's start from the typical map sophistication that we have already seen before. So we need to add a precondition saying that for every character in the list, it has to be either in the own state or the offer state, because we now need the ownership of the element. And then in the post condition, we are going to update the character. Depending on its state, if it's own, then you stay as own, we just update the content. The same for offer, we are just going to update the content. And that's all the possible state in this case. And we can write it as a map into the borrowed state. We don't need to write the pattern matching all the time, of course. So now with the refined logical model, with the refined representation predicate, with the enriched API sophistication, we can just need to prove the correctness of this program, which we have already seen before. So I just presented logical pinning, which is a borrowing model and proof discipline for precise reasoning about containing internal pointers. The key idea is that we have this fine-grained borrowing state that decouple pointer adjust exposure and ownership transfer. And we enable precise API sophistication by in the API, we can check the validity of these exposed internal pointers. And in the paper, we have much more. For example, if you're curious, can we borrow recursive substructures? Yes, we can. We can borrow the tail of the list. We can borrow subtrees. And then we also show maximally precise sophistication of a realistic API, list API. By maximally precise, I mean that the API, they account for all the possible internal pointers. And they also require minimal ownership in the precondition. And then we also show the comparison to match 1 to Ross borrows. And then we also show how logical pinning assume well-known proof patterns. And also we show you how to do systematic transformation from a normal container to a container with borrowable substructure. And finally, there's some nice composition between the predicate transformer, the little b and little star here, to allow you to express some subtle case like, I want to borrow the intermediate pointer and transitively borrow the tail, or I want to just borrow the tail itself, or I want to be able to borrow both, but separately. Like you can express those subtle cases. And you can scan this QR code here to see our repo, to see our formalism. And thanks. I'm looking forward to your question.
I wanted to ask, why do you have a list after offered and borrowed? What's the reason for having multiple aliases if presumably they're all pointing to the same location?
Yeah, I actually have a backup slide for this. Sorry, too far. Sorry. Here. Wait. Okay. The problem is, so we check a list of alias because like the list actually encapsulate all the equality, so that we don't need to check them separately. So for example, if it's already offered, of course we can say that just return the pointer that we already know. So we can check that separately as another pure condition by the side. Or we can just say that it got added into the alias list. So that our specification is actually very simple. We just say that we pin it down again on a new location it doesn't matter if it's already got pinned down in one location or not.
Yes, but when you move from offered to borrowed, don't you have the constraint that you can be borrowed by only one pointer?
When I move from borrow to offer to borrow, yeah, I will need to from offer to borrow. I will need to forget about all the exposed internal pointer. But it doesn't matter like how many of them because they are all equal to each other.
Okay, so in a language like C++, you have iterators, so they can be invalidated, which is kind of similar to what you have shown, but more importantly, they can be moved around along a list, next and previous cell, and it is not clear if this is a use case you can support with your model.
So if I understand correctly, you are saying that you have a value that you can move in the memory? Or I didn't quite get the question, sorry.
Yes, say if you have a pointer to a cell of a list, of a doubly linked list, you can move the pointer to the next element or the previous element.
Mm-hmm.
And is it something that you support with your model?
Yes, you can. In the API, we support like the API support that go to the next element, the previous, or even the next tail, the nth element, something like that.
Thank you for the talk. It was very nice. My question would be, if you have like borrowed the pinned down and borrowed a pointer, can you insert it into another logical list as well, and then pin two elements of the two lists together, or is that not yet possible?
So currently, if two lists want to share a common element, is that what you mean, right?
Yes, but if you have it pinned down, you kind of know that you can keep it and you can like switch borrow it around.
Yeah, exactly. That's one of the use case here. If we have multiple containers that share one element, like usually temporately, we will view it as one view it as offered at that location, or the other view it as borrowed at that location.
All right, so you can actually have
yes,
two logical.
and that's yes, exactly, and that's one of the. For example, when we do tree rotation, that's what happened because in the middle of tree rotation, you have two nodes sharing the same subtree. Yeah.
So let's thank the speaker again.